All right, folks. So we've talked about the heat capacity of a bolt. We did a lab where we boiled this bolt for 5 minutes and we tossed in a cup of water. We got that final temperature, all that good stuff. And then you guys did a Q to Q calculation. That's what we call these, to find the C of that bolt. And the key idea that this was surrounded by was the fact that the Q of the water, that is the heat energy that the water gained, must have been the exact same number as the Q, that is the heat energy, that the bolt lost. So the water's temperature went up, and the only reason that that happened was because heat energy must have been going into that water, and that heat energy was coming directly from the bolt, which was at a much higher temperature. And energy from the bolt continues to go into that water, raising that temperature until they both meet at the same temperature, somewhere in between where they both started. So we're going to go ahead and try another heat capacity problem here, where it's the exact same lab, but it was done with pennies. So this is like a lab handout where you are just given the data that a person collected during the lab, but you need to know what to do with that data. You'll absolutely need to be able to do this on a test. So let's go ahead and break this puppy down. So this person, they took the pennies, they boiled them for 5 minutes, they toss them in a cup of water, and they get the temperature of the water before they toss the pennies in, and temperature after they toss the pennies in, and that's that. So first of all, we want to get the mass of that water. It's 60 milliliters, so because water's density is 1 gram per milliliter, this should be close to 60 grams, but we want the exact mass to work in our Q equals mc delta T, that M part of that equation. We want the exact mass so we can be really precise with our calculations. So what we're going to do is we're going to find the difference between the cups when they're empty and the cups when they're full of water. Okay, so that difference between 68.35 and 9.25, that'll tell us the mass of the water that's in there. That comes out to be 59.10. So that's what we put there. So that's one part of the data chart that you may not be given, but you have the information you need to calculate that. In the meantime, I might as well get the delta T of my water over here. That's the difference between the final temperature and the temperature at the beginning. Well, 5.9 degrees. And as I mentioned, the big idea here is that the Q of that cold H2O in the styrofoam cups will be equal to the Q of those pennies. Okay? The heat energy that the pennies lose is the exact same energy that that water gains. Remember, energy cannot be created or destroyed. Energy that disappears, quote unquote, from one thing, the pennies in this case, must have gone somewhere. That would be the water in the styrofoam cups. So let's go ahead. We see that the Q of the cold, H2O, is going to be the exact same as Q of the pennies. So if we calculate the Q of that cold H2O, because we know the mass, the specific heat capacity, and the delta T of the H2O, in other words, we know the M, the C, and the delta T. So we can calculate that Q. So that's exactly what I'm going to do. The Q of that water will be the mass of that water, which is 59.10. Again, mass of the water, not the penny's mass of 49.50, the mass of the water. The C of all liquid water is 4.18. And the delta T, as we already calculated up there, is 5.9. So that tells us that the water gained 1,457.52 joules. So that's the heat that the water gained, which should be the exact same Q, the heat that the pennies lost. So we're going to take that value and we are going to bring that over here. So now that we know the Q of the pennies, we can set that equal to the M, C, and delta T of the pennies, and we can solve for our C. So here's the Q of our pennies. It's the exact same energy that the water gained. The mass of those pennies is 49.50. Again, notice that we used a different mass this time. We used the 49.50 of the pennies, because we were talking about the Q of the pennies, so we need to use the M of the pennies, and the C of the pennies, which is what we don't know, so I'll leave that as a C, and the delta T of the pennies. So we can't use this delta T of the water, again, the 5.9 like we did before. We need to calculate the change in temperature of the pennies. So if you think about it, hey, right when you take that burning bolt from lab the other day, right when you take that bolt out of the water, you don't want to touch it, right? Why is that? Because it's super hot. How hot? Well, it's at exactly 100 degrees Celsius because it's been in boiling water for 5 minutes, and boiling water is always at 100 degrees Celsius. So the initial temp of your pennies is 100 degrees Celsius. You toss them in the cup. they send energy into the water until the water and the pennies reach the same temperature, and there is no longer a high and low temp. It's just all the same. And so the pennies were at 100. The delta T of those pennies was 100, and they went down to the 25.8 here at the end. And so the delta T of your pennies is 74.2 degrees, and that is what you use right here for your delta T. So we're towards the end of our problem here, so I'm going to simplify. Here's your Q equals, I multiplied my M and my delta T, so 49.50 times 74.2 is 3,672.9. We're still multiplying by C because we don't know what that is. And to get C alone, on the right-hand side, you have to divide both sides by 3,672.9, which is what I did. And when you do that, so 1,457.52 divided by 3,672.9, that'll come out to be 0.397 joules per grams degree Celsius. Remember the units there, joules per grams degree Celsius. And that is the C value of the pennies specifically. So there you go. That is how you do a specific heat capacity calculation, specifically using this Q to Q strategy where you take the Q of one thing and set it equal to the Q of another when you know that there's a heat transfer going on. So again, the Q, the heat energy that the water gained, must have been the heat energy that the pennies lost. So that's good practice for you there. I want you to try the other side of this worksheet where it's a similar calculation, just with a nail this time. And see if you can do this whole thing without looking at the answer key below. So see if you can go ahead and take care of this whole thing on your own. And please let me know if you have any questions. Again, a question or two just like this will be on your unit test, which is next Thursday and next Friday. So that's going to be October 21st and the 22nd. So make sure you're ready to play, that you understand this without any help. Okay, you guys have a good one. I'll see you.